want that in my video. Okay, so 1.4 continuity and one-sided limit. Continuity is continuous, whether it is continuous or not. So we're going to talk about those two things, and you're going to be describing continuity of graphs. Okay, so we have three graphs up here. This is discontinuous. See the hole in the middle? Okay, now the open circles at the ends don't count. Okay, it's continuous over a domain. Got it? So our domain is from the A to B. See that? But it has one discontinuity. See that in the middle? It is called a removable discontinuity because it's one little issue. Here's how you remember it's removable. Watch my finger. Did I remove it?
Yes.
See?
Wow.
And it comes back. Okay. So that is called a removable discontinuity. It's one little hole in the graph, nothing else. Okay? You can just imagine you have your finger and you go boop and it's filled. So that's why it's called a removable discontinuity.
Why is it AC?
Those are just letters on the bottom. Okay, it's also called removable because that's what would occur if I reduced a quantity out of the denominator. There would be a little hole in the graph, okay? You removed it from the function. So removable discontinuity is just a little hole. The next one is a non-removable discontinuity. Can you see the difference in the pictures?
Yeah.
Okay.
Because if you put your finger over it, you can still see
You can still see it. Plus, the removable, remember, it was continuous from A to B, except for that point, right? Is the second one continuous from A to B?
No.
No, it has a big, huge break, doesn't it? Okay, so the second one is called a non-removable discontinuity. You can't fix it. You can't just plug the hole. Now, I'm sure there's more technical terms, and somebody might be really upset with me that I describe them like that, but that's what I do. Okay, the last one is also a removable. Even though it looks like that, it's removable because it's just one little hole. Okay, the third one, see that?
Mm-hmm. Yes. Is it because they meet together?
Yes, they are.
So if they don't meet together,
It's non-removable. Yep.
But if they meet together,
Right. If they are continuous at all points except for one, they are removable. Make sense? Because the first picture and the last picture, they're continuous except at one single point, aren't they? But the middle, they're discontinuous at more than one single point.
What would the black dot be on?
It
Like,
just
what is
would
it
be.
It
It would be like the limit. Like if we did from the left, it'd be one thing. From the right, it'd be one thing. But add it would be different. I mean, it's just showing you a different kind of graph.
seriously?
I don't know why I felt the need to keep my arm up there, but I did.
Do we need the writing that they put? Like,
I'm gonna explain. It's something different.
Okay.
Okay, my box. You guys ready for the box? Okay. It says continuity. This is the definition of continuity. Okay. We've got removable and non-removable discontinuities. Okay, those are discontinuous points. Now we're going to talk about continuous points. So continuity at a point. If a function f is continuous at c, if the following three conditions are met. F of c is defined. So c is some constant. Okay? So if I can plug in c and it's defined, it's continuous. Okay? If the limit of f of x as x approaches c exists. Okay? And if the limit of f of x as x approaches c is equal to f of c. So that means that there's no holes in anything. Does that make sense? There's no holes. all of these up here, are they continuous functions?
Yeah, no.
No, they are not.
Wait, why?
Because we're going to put this in. First of all, we're going to look at the first picture, okay? F of C is defined. So C is this point right here. Right here. Yes?
Yes.
Right here. Is it defined?
No.
No. So it's not continuous.
Is that
Wait,
because
why is
it's-
it not defined?
does not
Because there's a
exist at
hole.
that point?
Okay.
And if there's a hole, it's not included, correct?
Yes.
Okay. So this is not a continuous function. It is continuous function at every point from A to B except at where? C. And it is a removable discontinuity. Okay? Make sense? Okay, now I'm going to go to the next one. F of C is defined. If I plug in C, do I get an answer?
Yeah.
Yes? I get an answer. It's right here. Correct? Check. Check number 1. But all 3 have to be, don't they? So number 2 says the limit of f of x as x approaches C exists.
No, there's
So
numbers.
they're 2 different values. So does it exist?
No.
No. That one fails at number 2. Okay? Number 3. So we're going to go. Does f of C, is it defined?
Yes.
Yes, because we got that hanging chad right there, right? Okay. Is the limit of f of x as x approaches C, does that exist? It does, and it's the same thing, correct?
Oh, yeah.
The limit, because from both sides it exists, yes?
Yes.
Okay, the last one. Is the limit of f of x as x approaches C the same as if I plug in C? If I plug in C, I get what? This random point down here, correct? But if the limit is where? The limit's up
It's
there.
not the same.
So are they the same?
No.
No. So if any one of these 3 fails, it's not continuous, and you have to tell me if it is a removable or a non-removable discontinuity. Make sense now?
Yeah.
Okay. So I wouldn't write all of that. You just, those are the 3 conditions that have to be met. So the pictures were an example of getting further in the process, but just not quite making it. And then it just says continuity on an open interval. A function is continuous on an open interval from A to B if it is continuous at each point in the interval. A function that is continuous on the entire real number is everywhere continuous, which is kind of a does statement, correct? Now, what if I said, is the first function continuous between A and E?
Yes.
Yes. Yes?
Yeah.
No, yeah.
Okay. Is it
Dot
continuous
after.
between E and B though?
No.
No. But if I put one over here and I call this E, would it be between E and B?
Yes.
Yeah. Okay. What if I just cut it right here? Just cut it right there. Would I be good?
Yeah.
Yeah. No, if I cut it right there, I'd still be good, wouldn't I?
Yeah.
Okay. So does it depend where you cut your interval? Yes. So it's going to give me, remember, intervals look like they're x values, yes? So you're going to get intervals like that and intervals like this. What do these brackets and parentheses mean?
Included, not included.
Included and not
Which one is
included.
included?
The square bracket. Yeah, just the bracket, I guess I should have said. Okay, so discuss the continuity of these graphs. Okay, so we have the 3 conditions in the front, in the first page, yes? Yes?
Yep.
Okay, so it's not telling me a domain, so the domain I need to discuss is all real numbers, yes? Unless it states a domain, we are assuming it's all real numbers. So, what is the problem with A? F of x is 1 over x.
It doesn't. It's not defined because the x is in the denominator.
Well, there's an issue with one number,
0.
0. X can't be 0, can it? Because that would make the denominator. So my domain Gosh darn it. My domain we need to think about is x such that x is not equal to 0, correct? Yes?
Mhm.
So it is at a, what kind of discontinuity is that? Is that a removable or a non-removable?
Removable.
I don't know how you tell from that.
Okay, well, this would be an asymptote, wouldn't it?
What would be?
A 0? It's not reduced. I didn't reduce it, did I? This 0 would be an asymptote of this graph, correct? Yes.
I don't know.
Okay, anything less than the denominator is an asymptote. We went over this for like 3 weeks last year, guys.
Okay.
This graph would look like this. Yes?
Mm-hmm.
Okay, can I fill this hole on this asymptote? No. So what kind of discontinuity is it?
Non-removable.
It is a non-removable discontinuity. Because it's there, it is an asymptote. So it is a non-removable discontinuity. Oops, that's a Y. At x equals 0. So you need to be pretty descriptive. You need to tell me where it happens at. Okay?
So how do you know what we're looking at?
You're looking at the graph of that function. You should be able to picture that. I did not reduce anything out, so it is not a hole. It is an asymptote. And an asymptote would be something that would be non-removable, correct? If you go back to your other pictures and think about what they were, an asymptote is not, it's non-removable. Okay? So the next one I have x squared minus 1 over x minus 1. So the first thing I should do with this is what?
Factor the top.
Factor the top of x minus 1 and x plus 1.
You can reduce out, reduce out x minus 1, x minus 1.
Okay, I can reduce out x minus 1 and x minus 1. So I get an equation that is equivalent to the first, like that question I had on the quiz, right? X plus 1. But the domain is what? X such that x can't equal what?
1.
1. Okay, it can't equal 1, but it's not an asymptote, was it?
No. 'cause
I
it's
reduced
not.
it out. So this is a removable discontinuity at where?
At 1.
At x equals 1. Because you see how I removed it? Like we reduced it, I removed it. See what I'm getting at?
Mm-hmm.
Okay. So this domain is x is less than equal to 0 or x is greater than 0. So that means it's the whole thing, right? It's everything. Negative infinity to positive infinity. So now we probably need to sketch a graph of it so we can see because it's a piecewise function. Remember, piecewise functions, we do one function and we do the other, right? We don't do them all at one time. So we need to sketch a little graph. Well, the first one is linear that has an x-intercept at 1 and a slope of 1, correct? So it's going to go up, and actually it has a y-intercept of 1 at negative 1. So it's going to look like, if you don't know what that looks like, you need to plug in 3 points and graph it, correct? If you don't know how to get that, you plug in 3 points and you graph it.
Any 3 points.
Any 3 points, 0 or less, because its domain is from 0 or less.
Is this x plus 1?
Mm-hmm. Okay? Its domain is anything less than 0. So you can plug in 0. You would definitely plug in 0, correct? And then 2 other points to the left. So the next one, what kind of shape is this next one? It's x squared?
Oh, it's a square root. No.
It's a parabola.
Yeah.
Yeah.
It's a
that's
parabola that moves up what?
1.
1. So it actually starts the same place the other one left off, and it looks like what?
Up.
We don't know
Oh.
exactly what it looks like, but it needs to look curvy, a little curvy, correct? Because this is a parabola, isn't it?
Mm-hmm.
Okay, so we have a graph. Is it continuous?
Yes.
Yes.
Yes. Are there any discontinuities?
No.
Nope.
Is that
So
how
it's
you do
continuous.
all of those? Make the graph and then
Well, we didn't make a graph. Like here, I made a graph to show you,
Yeah,
but
I
you
mean
shouldn't
the,
need to.
the
Like some of them
specific
you need
ones.
to, and some of them you don't. Any piecewise functions?
Yeah.
I would. Continuous over. And what does this double backdoor mean?
All real numbers.
All real numbers. The other thing you could look at, guys, you wouldn't have to do this. Right here, if there's any gaps, see it's zeros included here, but not here, yes? See that? Okay.
Oh, yeah.
So as long as that helps you, okay. The other thing is you do need to know if they equal the same at 0, then you know they intersect. If they don't equal the same thing at 0, then that would be a discontinuity. So, okay, sine. You should know what sine looks like.
It starts
Where does it start?
at the 0.
Starts at the 0 and goes,
Oh yeah. Mm-hmm.
yes, and it goes
Yes.
up to 1 and down to -1. Any holes or breaks of that?
No.
Nope. So what's your answer?
Continuous over all real numbers.
Oh.
Continuous over all real numbers.
Is it all real numbers if it
Mhm.
only goes to 1?
No, that's your range.
Mhm.
We're talking x values. We're talking domain. We typically describe graphs in terms of your domain because if I know a domain, does the range automatically come with it?
Yeah.
Yeah. Am I good? Yep. You good? Okay, so I've alluded to this part for a while, and we've talked about the limit from the left and the limit from the right, haven't I? But we haven't said it. So in our title, we had one-sided limits, correct? So one-sided limits. This one, can anybody guess what this is from the left or the right? If you look just down at the box. Can you see it?
Right.
It's from the right. Why do you think it's from the right?
Because there's a positive.
There's a little plus.
Yeah.
And guess what from the left?
Negative.
Negative.
numbers.
And it's not in front of it, it's where? Behind it. It's not a positive or negative because it's behind it. Okay? So we're asking, when it says this, the limit of f of x as x approaches a constant from the right. I only care about from the what?
Right.
Right. And when it has the little negative, I only care about it from the where? Left. They are one-sided. Everything so far we've been having, they both have to be the same from the left or the right, correct? Now we can ask from the left or from the right. Those need to be bigger, don't they?
What?
Oh, would it help if I shut off the light?
I can see it
Is that better though?
a little bit.
And every year I have somebody say, well, why isn't it where it's supposed to be? It's not a positive or negative, is it?
No.
It's just telling me left or right. Make sense?
Yeah.
Okay. Hopefully you're not drawing a picture.
Oh.
I just think that would take too long for me. That would be too much. Yep. Tell me when I'm good to go.
I'm done.
Done? Okay. So guess what we're going to do? Actually, this only says from the right, but we're going to do them all. Just so we can. Okay, so I need, and that is a circle that looks like an Easter egg, but it is a circle. I love how it squishes it up when I put it on the screen. So I need to get the limit of the square root of 4 minus x squared as x approaches negative 2 from the right. Okay?
Wait, give me a second. Yeah.
So we're gonna do it from both the left and
We're going to start with the right, though.
okay.
Okay. So, approaches negative 2 from the right. So that's this way, correct? What do I get? No. What's my y as x approaches negative 2 from the right?
2.
0.
0.
Oh yeah, sorry.
So then I want the limit as x approaches negative 2 from the left.
0.
It is also 0, isn't it?
Mm-hmm.
Yep. So then I want the limit as x approaches negative 2.
0.
0.
Okay, wait, let me write that all now.
Okay. In order for the limit at negative 2 to exist, doesn't the left and the right have to be the same? Mm-hmm. Yeah, because we talked about that. If it's not the same from the left and the right, it doesn't exist at the point, does it? Make sense? There's a lot of theorems, and one of them is going to say exactly that. So when we go through them, you guys really need to be careful what you write. Because if you're writing too much of their words, is it going to confuse you when you go back and read them? Yeah. So does it make sense if I tell you from the left and the right, they have to be the same for that to exist at it? Yeah. We've already basically said that, haven't we? One of the theorems is just going to tell you that when we've already seen it. You guys have to let me know when you're good. Shelby, I do have a pencil sharpener, you know.
Okay. Oh, okay. We're good.
Are you sure?
Yeah, I just need to erase. Yep.
Okay.
Wait, so from the right would be the first one, right?
Yep.
There you go.
Okay. So I want the left, the right, and I'm not going to write out the whole thing. I don't know if you guys want to write out this whole example either. Just watch it. That's a lot to write. Okay, the limit, and I'm just going to write f of x this time, as x approaches 0 from the right. Now, this is called the greatest integer function. It looks like a step function, doesn't it? Mm-hmm. Now, what these are used for is I own one car until I own 2 cars. Does that make sense? Mm-hmm. There's no in between, right? I have one kid until I have another kid. Things like that.
Would it be 0?
Okay, so 0 from the right. So I'm approaching 0 from the right. I get what?
0.
0.
And from the left.
Oops.
No?
Nope. The limit of f of x as x approaches 0 from the left is what?
No.
Negative 1.
Why is it -1?
Because where I'm at, I'm not asking at 0 yet, am I? As I'm getting closer to 0 from the left, I'm still where? As I go here, aren't I still at -1?
Yep.
-1, -1, -1, -1, -1, -1. I'm still -1 until I'm where? At 0. See that?
Yeah.
Okay. So from the
Why wouldn't the other one have been like?
okay, so the other from the right, I was up here and then I went where? Down here and then I went where?
Oh.
Down here. So as I'm getting closer, you see that now?
Yeah.
Okay. So now I need the limit of f of x as x approaches 0.
0.
No,
There is none.
there is none. Why? Why does it not exist?
On 0.
No.
There are two and one.
There are two. Y is approaching
Two different values.
2 different values.
No abbreviation.
No. Okay. We've gone over this already, haven't we?
Yeah.
It's 1 from the right, it's 0 from the right, it's -1 for the left, so that means at doesn't, if you go back to your initial conditions,
If they're not the same.
if they're not the same, it doesn't exist. And this isn't continuous either, is it? And these would be non-removable discontinuities, wouldn't they? Because I can't fix them. They're not just something I factored out.
How do you know it's not just something like by the picture you can tell that? Like,
Tell what?
because earlier when we said like it was non-removable or
Mhm.
because there was nothing we could factor out of the equation.
Right, but this we don't have. Well, this is... The equation is this. I mean, this is the equation. There's nothing to remove from it. We
Oh.
can't simplify it.
Okay.
And this is what it looks like. And these are not continuous. So they're non-removable discontinuities.
They're not continuous because
There's
of the
huge,
circle.
there's huge, well, there's huge breaks. You go from 1 to 2 to 3. There's nothing connecting
It's not
1
a
and
continuous
2.
line.
There is nothing connecting from here to here and here to here and here to here. Now, if I asked you from 2 to 2.5, sure, it's continuous. But over the whole real numbers, it is not continuous. Okay, I want to see how far we got to go. Okay, this is theorem of existence. We just went through this, guys. This is theorem of existence. If the limit exists, that must be equal from the left and from the right. Is that not what I just showed you? Yes. That is all this theorem says. If let f be a function and let c is a constant, L is the limit. The limit of f of x as x approaches c is L if and only if it is the same from the left and the what? Right. You already know this. We already did this in, what are we on? 1-4, right? We already did this in 1-3. In 1-3, I told you that if they weren't the same from the left and the right, they're not the same, correct? All they did is they put the little symbol in out. You already know this.
Okay, so we should, if I want to write that down, I should write.
If the limit exists, if the limit of c exists, then from the left and right, they all have to be the same. The limit from the left, the right, and at have, like, for the limit of c, I don't know. They have to be the same from the left and the right. You've talked about that. You know it has to be the same value, correct?
Yes.
Okay, the next one. A function f is continuous on a closed interval. Remember how I keep talking about, ooh, if I change the interval to here, it works, and not here? This is it. Okay? It's on a closed interval from A to B. A, B. Here's my picture. If it is continuous on the open interval of a, b, that means that the limit of f of x as x approaches a from the right is f of a. And from the b, the right, is f of b. It just means it is continuous. Yes? There's no holes. I can use direct substitution. Yes? We've gone over this before too. All they're doing is writing it in terms of the left and the right. That's it.
So technically we already know this, so we wouldn't necessarily have to write it down.
Right.
Okay.
But you notice that it doesn't discuss what happens on the left of A, doesn't it? It is not discussing what is happening over here of A, is it? And it's not discussing what's happening over here on B. It's only what's in here. Because it says it's continuous there. Okay?
So there could be a bunch.
It could be a break over here. We don't know. We're only right here. Just like on those last pictures, I said, oh, what if I just look right here? Then it'd be great. And we did that with trig last year. We'd say, oh, we don't want to let that. That doesn't work for us. So we cut it off. I got one more slide for us, and that's it. And that covers everything we need for today. Shelby, you let me know when you're good.
Okay. Give me that one.
Maddie, you good? Okay. You picked up your pen. I was like, oh, no. Okay, this one just says discuss the continuity between the interval now of -1 to 1.
Continuous.
Okay?
There are no breaks.
So let's see. We're going to test it. Okay? It told me that the limit, it's going to move on me because I didn't hit my pencil. It told me the limit as x approaches -1 from the right of f of x, we have to have some equal things, right? Okay? So what is it as it approaches -1 from the right?
0.
0. I said right. Eh? And the limit as x approaches 1 from the left?
0.
So is it continuous?
Yes.
Therefore, f of x is continuous. That's pretty good for everything not working for us.
Mm-hmm.
We got it. Continuous over what interval?
Why?
Nope.
Oh.
-1
Oh.
to 1. Now I have to be specific because I only checked -1 to 1, didn't I? I didn't check anything else. So this is my proof up here, yes? Semicolon for Shelby. Therefore, f of x is continuous over -1 to 1. Okay? And that's all you're doing, their left and right hand limits today.
Under second